if if you've got the wrong numbers here. I'll come back to that. That's what is going to be happening with the rainbow. Here's your water droplet up in the air. Sunlight coming in, basically white light. It's all the wavelengths. As it goes into the raindrop, the violet bends more than the red does. Because it has a bigger index and therefore goes to a smaller angle. Now, bending more means it's gone to a smaller angle. As you go from air to water, it's bending closer to the normal. And therefore, it's a smaller angle at that point. But then when it gets to the other side, the angle that they're hitting this water to air thing gives us that index times the sine of that angle becomes bigger than 1 at that point. And so it doesn't go out into the air, it actually just reflects. And so you have a reflection going on here. And when it does, they cross paths. So now the violet's vertically is on top and the red's on the bottom. Now when they come back out, you got the violet coming this way, you've got the red coming like that. And so if you're over here and you're seeing the violet from the rainbow, you see that, but the red coming from that same raindrop is hitting below your eyes. You can't see that, not from the same raindrop. Where you're seeing the red come from are raindrops that are now higher. So you see the violet coming from lower set of raindrops. You see the red end of the rainbow coming from the higher raindrops. And so when you look at that rainbow, the arc going across there, the violet is on the inside of the arc, lower, and the red is in a higher position. And so where are you seeing those come from? Like the other thing with rainbows, if you think about it, where is the sun when you see a rainbow? So it's basically always behind you, or at the very least to the side, but behind and to the side maybe. And so if you've got those water droplets in the air, but they're in front of you, you see that sunlight coming, going into the water droplets, reflecting, coming back out, but it's dispersed all these different wavelengths, and you've got different than the rainbow there. And if you're in the center of that arc, then the violet, the lower wavelengths, which have the bigger indexes, they're at a smaller angle, and the reds are then at the bigger angle, whether it's straight up or whether it's to the side. The biggest rainbow you'll ever see here on the ground goes from like that, horizon to horizon, or ground level to ground level. Why can't you see the entire circle?
The ground gets in the way.
Ground gets in the way. Can't see it. If you're up in an airplane, though, it is, at least theoretically, it is possible. It has been seen multiple times. My wife says she saw one. I couldn't see it because she was beside the window in the airplane, and I couldn't see enough through the window to see it. She was looking out. We were flying from, I think it was Portland one time, back to Houston, and going over some of the Cascade Mountains up there. And there had been some rain, and she said, "Oh, there's a circular rainbow." I'm a physicist. Why can't I see it? But anyway, but you can see it there because now you're up in the air and the horizon doesn't get in the way, and it's possible to see that complete circular rainbow then. We actually saw one up in Alaska, but it really wasn't a rainbow as such, where the rainbow is the light coming from the sun, going into the water droplets, reflecting back out in the same direction it went in, and you're getting this rainbow effect. What we saw was, as you look toward the sun, and you couldn't see the colors totally, but you saw this circle going around the sun. There's the sun. And you saw some colors on what would be the top and then the bottom of that circle. The sides were more whitish. They didn't get everything there. And I didn't know what that was at that time. I knew all about rainbows, but what is this? Because you were looking toward the sun. So the light had to be going through something that was dispersing it. After I got back to, this was like in May or early June of that year, got back to school, got a book on, light phenomenon that you can see in the sky. And I looked it up, and what's happening is in the upper atmosphere where it's really cold, by the way, the sky looked completely clear. But even then, you've got water vapor that can be up there, and it forms some ice crystals. And these ice crystals then very light, and so just any air you've got up there at all, air currents can cause it to basically hover up in the atmosphere. They might fall down a little bit, and then they get pushed back up, that sort of thing. But you don't just see them like you would a cloud. But those light crystals then are acting like prisms. If they're in the correct shape, and they're, the wind is keeping them in the right orientation to the sun, then they act like prisms, and the sunlight goes through them and creates the rainbow effect, the dispersion of the light. Then you can see that circle going around the sun. In this case, that case, you're looking toward the sun. A rainbow, you're looking away from the sun when you see it. Another thing I remember, another time my wife and I were driving and we see this nice rainbow. When you see the rainbow, if you can, you may not see a complete arc, but if you mentally form a picture of the arc that would be there, you're going to be at the center of that circle, of that rainbow arc. You're right at the center of it. If there's water drops in the right place, then you can see the entire arc going across. But anyway, that comes about because of different indexes of refraction for the different wavelengths. The main arc of the rainbow, you've got the one reflection going on inside, violet through red. Sometimes you'll see a second rainbow. It's called a secondary rainbow. The lower one would be the primary. Secondary rainbow is occurring, sunlight comes in, so here's your violet and red, and there's a reflection. You got now violet, red this way, and then there's another reflection. Anyway, so the red should be on top, violet on the bottom. And so the red's coming out at a smaller angle, and now the violet at the bigger angle. And the color are reversed in that secondary rainbow. And it's a double reflection going on inside the raindrop at that point. Maybe while we're doing the lab today, I can clear it up. I've got a picture of a double rainbow. We saw it in Colorado one time, and you can see that happening. But anyway, So, different indexes for different wavelengths. If it's gonna get you to do anything with that, then the problem's gonna mention something about the different indexes, or give you more than one index for that. Otherwise, if it just says glass index of 1.5, then you're not really getting into what's happening with the different wavelengths. You're just thinking of it as a single wavelength with that index. Not looking at the different colors. But that's the basic law there, Snell's law. Think about that reflection where it doesn't go back out. If you have like air and water. Air, we're going to say the index is 1. Water, we're going to say it's 1.33. If you got a fish under the water, in order to see the fish down under the water, one thing, the water has to be clear. Don't run into that too often in rivers around here. But if the water's clear enough, there's the fish down under the water. Well, light has to hit the fish, and it reflects and goes back out into the air. So it comes this way, and then it's going to go from the water into the air because you're going to a smaller index. The theta 2 is going to be a bigger angle. So here you are, you're the fisherman in the boat, and you're looking down at the fish, and the light's coming to your eyes, so you see the fish down there under the water. Well, if this theta 1, say, is here, because I'm going to do several of these. If theta 1's 30 degrees, so the light coming from the fish to the surface is hitting the water at an angle of 30 degrees to the normal. What's going to be the angle on the air side? So what's the theta 2? So I have my 1.33 times the sine of my theta 1 is going to equal a 1 times the sine of theta 2. So for theta 1 of 30 degrees, and do an arc sine then, and that gives me now 41.7 degrees approximately. Well, but what if the fish is further away? So now to get to us, it's got to go hit the surface at a bigger angle. Okay, so it goes to 40 degrees. So, let's do one thing here. Sine of 1.33 times sine of 40. And that's going to give us something into parentheses, so delete that one and try. That's at 58.7 degrees. So as this theta 1 gets bigger, the theta 2 is getting bigger. If I go to 45 degrees, now I'm up to 70.1 degrees. If I do 50 degrees, my calculator gives me a complex number, A plus BI type of number. And unless you got a calculator that will give you complex number answers, then what you're going to get is it's going to say something like error. It's going to give you an error message of some sort. So do the arc sine of 1.33 times the sine of 50 on your calculator. What does that give you? Would you need that? Do 1.33 times sine of 50, and then do the arc sine of that answer. This gives you error. Because what's happening is 1.33 times the sine of 50 is 1.0188 divided places. But you can't have a sine bigger than 1. They don't exist. And again, some calculators will give you a complex type of answer for that. You could put it in complex form, but it's not a real number. So what's happening at that point? As this angle gets bigger, this theta 1 is getting bigger, then the theta 2 is also getting bigger. And when theta 1 reaches a certain point, then theta 2 is going to become 90 degrees. And if theta 1 is bigger than that angle where theta 2 goes to 90, then you get this, on this side, you get the sine of an angle that's bigger, sine bigger than 1, and it ceases to exist. And what's happening there is now, instead of refracting and going out into the second medium, it reflects. And you have what's called total internal reflection. Nothing is refracted, everything is being reflected. It stays inside the first medium. Now, that's when the angle on your first side is bigger than a certain amount, which is then called a critical angle. And that critical angle, so sine of the theta of the critical angle, is going to be the N2 over the N1. But it only works, you've only got this critical angle if N1 is bigger than N2. So if you're going from the bigger index to the smaller index, you can have this critical angle. If you're going the other way, then the angle of theta 2 is going toward the normal, it's getting smaller. And so it's not ever going to get to a point where you got the sine of the theta 2 is bigger than 1. It's always going to be something less than 1. But if you're going from the bigger index to the smaller index, it's like from water to air, you've got a critical angle at that point. And anything bigger than the critical angle, there's no refraction, it's all reflection. If it's less than the critical angle, you do have refraction going on. If it's at the critical angle, there's refraction, but it's at 90 degrees, so it's like right along the surface. That's the whole point in things like fiber optics. That's the way they work. Or that's the main thing in them. You've got, like, here's your, whatever the fiber is made out of, glass, plastic, whatever material. You got light going through the fiber. As it hits the side of the fiber, because the fiber may turn and do things like that. This angle that it hits it at, you always want it to be bigger than that critical angle, or the N1 being bigger than N2. And so it reflects, and then when it hits this side, it's bigger than the critical angle. When it hits over here, it's bigger than the critical angle. And whatever side or the angle it's hitting the side of the fiber at, you want that to be bigger than the critical angle. And the light stays totally inside the fiber at that point. So when the doctors do like a heart cath, they take that little tube, they put it in an artery down in your upper leg area, and they feed that thing up the artery, or or the vein or whatever it is, they're putting it in. They get it to the heart area, and then they can shine light, or they have a light basically on the end of it. It shines light, the light goes down the fiber to your camera, and you can take a picture of what's inside the artery. How much is it blocked? That sort of thing. So they do the heart catheterizations to figure out, do they have to do a stent, do they have to do heart surgery, whatever, to unclog the arteries. If you've got cable for your TV, as opposed to dish or something like that, you got the cable system. Most of them are trying to put in all fiber optic cables for their communications. Especially if you had new telephone lines put in the last 10 years probably. They're probably trying to replace all the copper wiring for telephone wires with fiber optic cables at that point. The copper wires work fine, but with fiber optics, because you're dealing with the frequencies of light waves as opposed to the electromagnetic or the alternating currents that you're sending through the copper wires, you can put a whole lot more information in there. Much higher frequencies, and therefore you can put more information into the fiber optic cables than you can into copper wire cables. You have 1,000 conversations going on in one fiber optic cable where it could only be, say, 10 or whatever in a copper cable. And of course, with all of our internet stuff nowadays, we want that because now we got more data transmission capabilities. So fiber optics, that's the whole point in that, is this idea of total internal reflection. Of course, in the fiber optic cables, you've got the index of the cable itself, you've got the index of whatever's outside it. They will actually maybe have a material around here that's at a higher index, still transparent, but it's a bigger or a smaller index than the N1. And then past that, there may be a very highly reflective material. So if anything happens to get out, it's going to be like a very silvered sort of surface. It reflects very much of it at that point to keep it all in. But the main thing there is this total internal reflection. You get these big enough difference in indexes, and at almost any angle they'll internally reflect. Okay, so that's total internal reflection. That's the idea there. When we do the Snell's Law lab, which should be the week after the next test, we'll try to measure that index of that critical angle for water and air at that point. But otherwise, it's just due to Snell's Law. But that equation does come from Snell's Law. You're saying the N1 side, if you're at the critical angle on the N1 side, that's equal to N2 times the sine of 90 on the refractive side. But the sine of 90 is 1, and so it just has critical angle is N2 over N1. Main thing to remember there is that for this critical angle, the N1 has to be bigger than the N2. So the index of the material you're in has to be bigger than the index of the material that your light's trying to go out into. It's the other way, there is no index, or there is no critical angle. Oh, and in real life, you've got reflection, you've also got refraction. Refraction and reflection at the same time. So like light coming in this index, refracts, goes into this index. There is some reflection also. that surface. So it's splitting the beam of light, at least to a partial extent. Sometimes more than others, depending on what the two mediums are. But there is both reflection and refraction. So now most problems we're dealing only with the refraction, or we're only dealing with the reflection. But could be either way. Okay, so that's Snell's law and talking about refraction, and that's, I try to get into lenses now, that's gonna take up too much time, so let's take a break, go to lab. We'll do the